All right, calculate the current output by the transformer. And so we have the AC generator. So the transformer, this is really the input to the transformer, right? And then that is the transformer output to the grid. And all we don't have is the current, right? So understand that, and this is our primary, right? Primary. This is our secondary. Only we don't have the current, the secondary current. Understand this, that in a 100% efficient transformer, power in the primary equals power in the secondary. Okay. In a 96% efficient transformer, the power in the primary times 0.96 equals the power in the secondary. Okay, does that make sense? So whatever the input is, right, times 0.96 is the secondary, and that comes from this, right? Efficiency is power output over power input, right? So the power output is E power input, and this is our power input. Primary is your input, right? Okay, and then the formula used for power is just I times V, right? So I primary, V primary times 0.96 is going to give you I secondary, V secondary. Here's your secondary voltage. Here is your primary voltage. Here's your primary current. Okay. Notice that K is times 10 to the third, right? So that's 25,000, 3.9 thousand. That's 330,000, right? So just be careful there. All right. Electrical energy is often delivered across large distances at 330 kilovolts. Identify the main advantage. Well, let's see. Remember that the power loss, well, I think one of the points you need to make is that the power loss on a power line is I squared R. Another, and then also the power is IV, right? So if you use a tremendous voltage, your current can be smaller, right? So maybe the two marks are talk about the relationship between current and voltage, right? Large voltages lead to less current being used, right? That's maybe one of them. And then two, it reduces the power loss because power loss is I squared R. In fact, it's a huge difference. If you can cut the current in half, it's 1/4 of the power lost. So anyway, all right.